Welcome grade 11s to our fantastic Monday show here at Learn Extra Live. You're here with me, Megs, and of course my lovely leading lady Dina. How have you been?
I've been very well, Megan.
I haven't been here since February, so please excuse me for my rusty mathematics skills, but I'm so impressed that I'm here today. So what are we doing?
We are doing grade 11s, a little bit on probability. It's a very, very short period to try and cover all the grade 11 or the whole grade 11 topic. So we'll be really looking at the aspects of probability.
Okay, thank you. Well, let me tell you, previous show I didn't tell you where to get all your information. Ooh, naughty me. So I just want to tell you, you can go onto facebook.com/learnextra, as well as Twitter, which is @learnextra. And I know you mindsetters want to be there with the notes in front of you, and you can download them at mindset.co.za/learnextra. And if you haven't noticed, it's spring day. I brought a bit of spring here into the Mindset Studios with my little headband. So hope you guys are amped and ready. And let's get started with probability. Grade 11s, don't forget, this show was proudly sponsored by Macmillan. So let's go.
Thanks, Megan. Right, grade 11s, you may have done a little bit of probability already in grade 10, or you may not have done some probability. So in order for us to all be at the same place, I'm going to revise some of the definitions that we use around this topic, and then we're going to work through some examples around two of the most important topics around probability, and that would be working with a Venn diagram and then also working with two-way tables, which are also known as contingency tables. So to get us started, we are going to be doing quite a lot of dense text work where we're going to look at the definitions that we're going to be using, because obviously any game that's played, you're required to know the rules. Without the rules, you can't really understand the game, and so that's where we're going to go. Just go and try and learn some of the vocabulary around probability. So let's get to the slides. As I said, in this lesson, we're going to revise the definitions used in the study of probability. We're going to work with some Venn diagrams, and we're going to use contingency tables to establish whether events are independent or not. The first definition that you will see around probability is the word experiment. We often talk about an experiment, and that is a situation that will involve probability that leads to results, and the results are called outcomes. So every time, for example, if you throw a coin and you get a head, that would be known as an outcome. If you throw the coin again and you get another head, that would be another outcome. So the total amount of outcomes would give you what an event would comprise. So your event might be, let's toss a coin 3 times. That would be the event. The outcomes would be, what options do you have available to you when throwing that coin? Let's look at what type of outcomes there are. So an outcome, just one, would be the result of a single trial of an experiment. So if I toss a coin and I get a head, that would be my outcome. I got a head. If I toss my coin and I got a tail, that would be my outcome as the result. The possible outcomes are all the possibilities that I can have. So for example, if I toss a coin, I can have either a head or a tail. So my possible outcomes are a head or a tail. And those possible, if we're going to work with Venn diagrams later, they're also known as the sample space. So the sample space would be all the possible outcomes that you can have of an event. So for example, if you were rolling a dice, you would get either a 1 or a 2, 3, 4, 5, or 6. So your sample space would be all the possibilities of the value of that dice. Those would be your possible outcomes. So a synonym for possible outcomes is your sample space. Now, this concept, probability, is really the measure. So once we've got we've identified what our possible outcomes are, we've identified what our sample space is, the probability is that value. It's a measurement of how possible that outcome can be. So in this case, how possible or how likely is the event to take place? So it is a theoretical measurement. It's not like, for example, with your weather, whether you wake up in the morning and you think, oh, today's going to be a sunny day, but later on it's actually going to be a cloudy day. You're not measuring a predictability of the event. You actually want a number that measures a theoretical likelihood of that event actually happening. So with your coin, with your dice, there is some measure that you can have in terms of how probable it is for you to get a certain outcome. How do we calculate this measure? So if this is a measure, then how do we calculate that measure? We can easily calculate the probability of an event occurring in situations where each outcome is equally likely. Okay, so when we toss a coin, we understand that that coin could have an equal likelihood of having a head or a tail. We haven't made the head have a lot more material on it, so it's heavier, so that when you toss it, you may always get the tail because the tail is lighter. So you haven't tampered with a coin in order to make one side of that coin become more probable. So when we're talking about the measurement of probability, we understand that the outcome is equally likely. The same thing with the dice. You're not going to put a weight on the number 6, so that when you throw the dice, you're not going to get either side being equally likely. And then there's a very special way of writing this measurement. This measurement is written with a capital P, which measures that probability, and in brackets you will always write down what event you are trying to measure. So P brackets, it's not like a function. This is not a function value. It's really a way of ordering our measurements of our possible outcomes. So we would have capital P and in brackets the event that we are measuring, and it will always be equal to, if we are measuring the event of the likelihood of a head happening, then that would be the number of possible outcomes that you've specified in the event. We're then going to divide it by the total number of possible outcomes. So if I had to toss a coin 3 times, for example, I could get a head, and a head. Or I could get a head, a tail, and a head. So I could get all those possible outcomes. You can then ask the question, what is the probability of us getting 3 heads? Then our number of possible outcomes in the event would only be 1, because it would only be one time that I would get a head, a head, a head. The others would all be different, in which case our total number of possible outcomes would actually be 8. So it would actually be a 1 in 8 chance of us actually getting that probability. Remember, probability is a numerical, a theoretical value that measures the likelihood of that event happening. And then if we take the sum of the probabilities of all the possible outcomes, we're always going to get a 1. So if we look at our coin, tossing it 3 times, if we took the probability of getting a head, 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 or a head, tail, tail, or a tail, 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 all those possible outcomes, if we added up all our probabilities, we will always get that to total 1. Right, then we've got a very interesting phrase, mutually exclusive events. Okay, I'll show you a picture in a while, but for now, this word simply refers to events that cannot happen at the same time. They would be known as mutually exclusive events. So if you had event A and event not A, these could not happen at the same time. Now, let's look at the picture first. Here is a sample space. We often draw, this is probability theory, we will draw the sample space in a rectangle, and we will draw the events that can happen in circles. This would be event A, and this would be event B. Because there is no, let's just do that a little bit better, and event B. Because these two events are not intersecting, because they are not overlapping, it means that they are independent of each other, and so we talk about these events being mutually exclusive. They cannot happen at the same time. Now, if we were trying to find out what's the probability of A or B happening, then we would talk about the addition law. If two events are mutually exclusive, then the addition says that the probability of A or B happening would be the probability of A plus the probability of B. Now, before we go on, I just want to clear up some language as well. Let's just go to the meaning of the word. The probability of A or B means the probability of A union B. Actually, I'm not even going to include the word probability at this stage because it's not really that significant. All I'm wanting to look at is that when I'm looking for the set that asks for or, then I'm taking all the elements. Okay, so you're going to see this quite often. The or is it's a little conjunction in English, but in mathematics it represents everything that you're taking. And so it's also known as the union. It's a union, and you sometimes see it like this. Okay, so all these mean the same thing. That's an English word, that's a mathematical word, and that is the in terms of Venn diagrams, it would be the union of two sets. Now, if you have, let's just go down, and let's say we have A and B. What do I mean by that then, if I use the word and? That means I only want the intersection, and that intersection is written as A, and it's an upside down U, a B. So that refers to the elements that are common amongst A and B. Okay, so if we said, let's set A be the set of even numbers, and let's set B, let's just write it down here. If A was the even numbers, and this were the odd numbers, then the union of all the sets would be all your natural numbers, for example. But the intersection of the two sets wouldn't exist because I don't have overlapping numbers that can both be even and odd at the same time. So if I was going to write my even numbers here and my odd numbers there, I would not get an intersection. However, if I asked you for the even numbers and I asked you to write down the prime numbers, so let's say, give us another example. Let's say A is all the even numbers and B is a set of all prime numbers, then this set here would have the numbers 2, 4, 6, 8, etc. And this one would have the numbers 2, 3, 5, 7, etc. And if I asked you for what is A intersection B, I'm saying which numbers are common to both sets. We talk about the elements in the set, so which values are common elements, and we can see it's only this value 2. That is both even and prime at the same time. So there's an overlapping value. Now, how would we write this using a Venn diagram? That's just using the set notation. We would have sample space first, and inside we would have an overlap. So we'd have set A, set B, and inside here we we've got the value 2. It's both in set A and both in set B, so the overlap indicates that. Now, I need to show you that, to show you how different it is when you do get an overlap as opposed to when two events are completely separate. So even numbers, odd numbers, they've got nothing in common, and those are known as mutually exclusive events. So let's get back to the notes, because the notes also explain this. Okay, so that's mutually exclusive events, no intersection, and that is always going to happen. Now, what happens if they're not mutually exclusive? Then the two circles will overlap, like I showed you just now. The shaded area where the circles overlap represents the event where A and B are taking place at the same time, and this, remember, the upside down is called the intersection. So let's look at that shaded area where they're happening at the same time. There it is. So again, we have a sample space, and we have set A, and we have set B, and in here is the area that belongs to both sets. If they're not mutually exclusive, then I will show you in a moment an example that shows this very nicely, but the probability of either one, either A or B happening, will be the probability of A plus the probability of B, but then we'll have to take the probability of, remember, this is the intersection. And why is that? Okay, we're going to do some work with a pack of cards, and we'll show you in a moment how that really works. Okay, well, I think that it's a good place to stop because I need to play cards with you, and it's going to take a while. So I'll hand you back to Megan.
Thanks, Dina. Hope you guys have a good break, and we'll be right here afterwards. Welcome back, grade 11s. I quickly need to talk to you about something because I forgot to mention it in the beginning. Bad, Megan. Yes, I know. But anyway, let me tell you, Spring School is happening from the 23rd to the 27th of September. See, Spring School, excited, get excited, because we're going to have live shows, exam revision, awesome teachers, as well as us, the presenters, here for you that whole entire week. So let's get cracking. We want to see your posts, your comments, and I will post where to find and check out the schedule, which will be happening from those dates on the page. So that's facebook.com/learn extra. But Dina has a lot to go through, so I'm going to hand over to her. Okay.
Thanks, Megan. And that last session just flew by very quickly. So let's play these cards much quicker this time round. Everybody's, I'm sure, has played with a pack of cards. I'm sure that none of you have not ever seen a pack of cards. How many cards are in a pack? Well, we have got 4 different suits. We know that we've got the black set, we've got the red set, and we have 13 cards per suit. So therefore, in total, we'll always have 52 cards. Those 13 cards in the suit have got the picture cards, and they've got the number cards, and we've got card 2 to 10 as your unnumbered cards, and we've got our jack, our queen, and our king as our picture cards. So in total, we've got 13. So we've got spades, we've got clubs, we've got hearts, we've got diamonds. So spades and clubs will be our black cards, hearts and diamonds will be our red cards, and in total, we have, for every single one of these, we're going to get a king, a queen, and a jack as our picture cards, and we get the card from 2 to 10 as our numbered cards. And so in total, we've got 13 cards per suit. Okay, because the next little question I'm going to do with you is to show you that probability of those events that are not mutually exclusive and the addition law from the probability of that condition or that situation. Okay, so if a card is drawn from, and remember, we're looking at a normal pack, so no one's tampered with a pack, somebody hasn't gone into the pack and taken away 2 cards. It's a normal pack, referring to the fact that there are 52 cards in that pack and that they have not been touched, so they are all of equal likelihood to be taken out of the pack. We want to calculate the probability of the following: that a card drawn at random, so I pick any card in the pack, I haven't specifically gone to a specific place where I know that card is sitting, And what is the probability of us getting a king? Okay, so let's go back to the theory. The probability of an event is defined as the fraction of the number of possible over your number in the sample space. So, number of possible outcomes. Okay, so the question becomes, the probability of us getting a king is going to be how many possible kings have I got in my pack? I've got 4 suits, I've got 4 kings. So that is my possible outcomes. What is the possible outcomes in the sample space? What is the number of possible cards that I can go and draw from? And I can draw from 52. So can you see how probability is a measurement of an event actually happening? I've got 4 possibilities out of 52, so my measurement becomes 1 in 13. So that is our probability, a theoretical value. Okay. Then, what is the probability of us getting a heart? So we do exactly the same thing. We say, what is the probability of us getting a heart? We want to know how many hearts do we get in a pack? Well, our hearts are our red cards, and therefore there are 13 possibilities of getting a heart. So these are our possibilities of getting a heart. And what is our total number in the pack? It's 52. So therefore, that's 1 in 4. So there is a probability, a 1 in 4 chance that I'm going to pick a heart. Okay. Then, what is the probability that I'm going to get a king and a heart at the same time? So, okay, what is the probability of us getting a king and a heart? Well, we've got to go to our cards. How many king and hearts do we get in our pack? Well, we only get 1 king in the heart section. So, whereas before we were looking at the 4 possible kings, this time around it's got to be a heart. We're now constraining what it can also be. So we can get only 1. And how many cards do we have in total? The total possible outcomes would be 52. So there's a 1 in 52 chance that the card you picked at random would be a king and a heart. Okay, so now we want to look at a king or a heart. Okay, so it's a king or a heart. So out of all the options, okay, we know that if you want the union of the two, it's going to be the same as what's the probability of having a king plus the probability of us getting a heart. But can you see that what's happening now is that inside here, my probability would be 4 out of the 52. My probability of the heart would be 13 out of 52. But this card is in there as well, because the hearts have got a king and the king has got a heart. So we've actually, that intersection of the 2 cards is being counted twice. So that probability doubles because we're counting it twice. So in order to undo that, we have to actually take the, so what you have here is there's my kings and they're my hearts. So this is my king and this is my hearts. And my kings, I've got 4 of them, but inside here I've got 1. So in here I've got 3 kings that are not hearts, and in here I've got 12 cards that are not kings. Okay, so in total, I have to take away this intersection minus the probability, and in order to just undo this, let's just rewrite it because I'm running out of space. So the probability of a king or heart is going to be the probability of a king plus the probability of a heart minus the probability of the king and heart. Okay. Otherwise, I would be counting it twice. And that is that rule that I showed you before the break, where the probability of one or the other happening when you've got an overlapping set, it will be the sum of the individual probabilities. However, we'll have to take away one of that intersection in order to only count it once. So what is the probability of getting a king in a pack? There are 4 kings, there are 52 cards. What is the probability of getting a heart? There are 13 hearts and there are 52 cards. And the intersection card is 1 in 52. So the probability of getting a king or a heart would be 17 minus 1, which would be 16 over 52. And we could actually use our calculator to round that off, divided by 52, and get a decimal value. So 0,3. 307, as a probability value is always sitting between 1 and 0, and yes, 16 over 52 is that value, but when it's written in decimal form, it's sometimes easier to just have that gauge. It's a 0,3 probability in terms of that range between 0 and 1 values. So this is a very, very good example to show you that addition rule when events are not mutually exclusive. Okay, so now let's go back to 1 and tell me what you think what is happening with this event. A bag contains 5 red discs, 3 blue discs, and 2 yellow discs. And a disc is drawn at random from the bag. Calculate that the probability that the disc is drawn is a red disc. Now, if you have the red, blue, and yellow discs, are those events are they mutually exclusive or not? I cannot take a disc and it cannot be 2 colors at the same time. We're assuming here that they're all red or all blue or all yellow. They're not a mixture of colors. So in that case, I would have my red discs, I would have my blue discs, and I would have my yellow discs. And since there is no intersection, those events cannot happen at the same time, hence they are known as mutually exclusive. So in the bag, there 5, 3, 2, there's actually 10 discs, and if a disc is randomly drawn from the bag, then the probability that it's red is we're going to ask ourselves, how many reds do I have? I have 5 red discs. What is the total number of discs? I've got 10, so I've got a 1 in 2 chance of getting one of those discs. What about the probability of it being a blue disc? How many blues do I have? I've got 3 blues and out of 10. So I've got a 3 in 10 chance. And then what about the probability of a red or a blue disc? That means the probability of red plus the probability of blue. So my red probability is 5 in 10. And the probability of blue is 3 in 10. So that is an 8 chance of picking either a red or a blue disc. So 4 in 5, for example. So mutually exclusive events do not have an intersection, so we don't take away that intersection. Okay. Now, there was something in the notes that we didn't finish. Let's just see here. Okay, and let's go down to number, I think we did. Right, independent events. What do we mean by independent events? If the outcome of the first event does not influence the outcome of the second event, then the events are said to be independent. Now, the event that we've just looked at, the bag with the colored discs in, if I take out a red disc, then I'm assuming that in my next random selection, I'm going to be using the same 10 disks. So we talk about that selection as being an independent event. Whereas if I had to take out the disk and I would be left with 9, then my next selection would be dependent on what happened to the previous one. And in that case, there is a dependency on what happens first. So independent events are events. Doesn't matter. First one can happen. It doesn't alter the second event. Okay. Now, events are said to be independent if the probability of one event occurring does not alter the probability of the second event occurring. Okay? And then there is a product rule for this independence, which we're going to use in a moment. And that is that the probability of A and B is the product of the probability of A times the probability of B. So if I can have that the probability of the intersection is the same as the product of the probabilities, then we talk about that we've got independent events. Okay. Let's just see our next slide. There we go. Okay. So let's see this coin being tossed twice. You've perhaps seen tree diagrams that show the possibility of the event occurring. And my tree diagram is going to have a coin being tossed. So we're going to have the first toss. We toss the coin. What are my options available to me? I can either toss a head or I can toss a tail. So since there are two options, tossing a head will be one out of two options. Tossing a tail will be one out of two options. Then I'm going to toss it a second time. If I do that, I could have a head here or a tail there. So again, there's still two options available to me, one out of two, one out of two. And in the second toss, if it was a tail first, then we get a head there and we get a tail there. So again, we have a 1 in 2, 1 in 2, which means what are our total outcomes? Okay, I have 1, 2, 3, 4 possibilities of outcomes. So getting a head or getting two heads would actually be a 1 in 4. This getting a head and tail would be a 1 in 4. This one here would be a 1 in 4. This one would be a 1 in 4. Now, tossing a coin is independent. So therefore, if I toss that one and then that one, I'm getting a 1 in 4 outcome. How does that work? Because a half times a half is a quarter. So the probability of a head and a head occurring, that intersection, is the same as the half times a half, which gives you a quarter. And therefore, that proves the independence theory.
Thank you, Dina. So mindset is I have something so interesting for you after this break, but I'm not going to say anything. We'll see you right after the break. Welcome back, grade 11. So, remember after the break I told you I had something very exciting to tell you? And guess what it is? Stars in Education Awards, guys. If you think you have an amazing teacher like Dina, I think you should enter them into this competition because you know what? It's for them. It's for them. Sometimes we forget that our education is because of them. So I think if you do have an amazing teacher, I've posted the link because it's too many PHPs, / and stuff. So I've posted it on the page, and I think you should go click and enter the teacher who's impacted your life. So don't forget it's spring day, hence the reason I'm wearing a band, and back over to Dina.
Thanks, Megan. Right, grade 11s, I'm hoping that you're enjoying this very numerical mathematics. It's all about numbers and working out theoretical probability values. We're now going to look at a Venn diagram to depict a scenario where we'd like to find out the probability of finding an individual event along, obviously, that context. So the scenario is as follows. In a grade 11 group of 65 learners, there are 5 learners who take science, life science, and geography, and 8 learners who do not take any of these subjects. 32 take physical science, 29 take life science, and 19 take geography. 13 of these learners take physical science and life science, while 8 take physical science and geography. So as you can see, there's a lot of overlaps, okay? And the best way to try and just sort out this data is always through some kind of visual representation. And our best one in mathematics is a Venn diagram. So best way to always look at this data is to go for the overlap of the 3 or the 4 or the 5 or however many events you've got happening, because from that point we can then work outwards. It's a lot easier. So let's read it again, because grade 11s, whenever we read something, we're just getting the context of the problem. We've seen there's 65 learners. We've seen that they take 3 different subjects. And now let's get to the nitty-gritty of the value. So let's read it again for detail. There are 5 who they take physical science, they take life science, and they take geography. So we know that these 5 are the overlap of the 3 circles. And then there are 8 that do not take any of these subjects. So where do we begin to visually describe this data is always with our sample space. We've got 65 in our sample space, and we've got 8 who do not take. So if a survey was done, 8 do not take any of these subjects. Then we know that, okay, so let's draw that first. We've got our sample space. And in our sample space, we have physical science, we have life science, and we have geography. So physical science, life science, and geography. And we found out that the intersection of all 3 is 5. So we can put it in the middle. They take every single subject. Okay, so the intersection of the 3. Now, we know that 32 take physical science, but how are we going to do that? Because some are taking physical science and life science as well. Some are taking physical science and geography. And so this whole circle tells me that there are 32 in there, but I don't know how many are in there. So let's go and find how many are in this overlap. Okay, so we do middle overlap, and then we do next overlaps to try and see then how many of these here take physical science. So what we're saying is that these 5 are taking physical science, life science, geography. Then these in here are taking physical science and life science. These are taking physical science and geography. So in here are only the students that are taking science only. So it helps us to really sift the data to determine what number of children are taking what subjects. Okay, so this for me is no good at the moment. 29 take life science is no good. 19 take geography is no good. But 13 of these learners take, this looks promising, 13 take physical science and life science. So this is the overlap between physical science and life science. There are 13 of them. Okay, and then we have 8 that take physical science and geography. So we've got the physical science and the geography. We've got an overlap of 8. Okay, now that's something we can work with. So let's go down. Okay, so they told us that the overlap between physical science and life science, this overlap is how much? 13. We were told that. So how many take physical science and life science only would be 13 minus the 5 would be 8. So in total, there are 13. Whoa, let's not do that, please. And if we have 5 already that are taking physical science and life science, but they also take geography, then we've got 8 that must be taking that. So it's important to understand what the overlap represents. This overlap represents everything together, and this overlap represents the physical science and life science. We were told that it's 13. We can't put 13 in here, so we have to separate the 5 that are already there with the 8, and together that gives us 13. Then they also told us that 8 take science and geography, physical science and geography. So we've got, in this overlap over here, we've got 8. which means 5 are already there, so therefore 3 students are taking physical science and geography. Okay? Now, the one overlap that they're not giving us, so if we go back, we'll see they haven't given us any other overlaps, they've just given us a total number of learners, is that they haven't given us this overlap over here. So in order to help us, we're going to make that x, because there's no way that we're going to be able to find out how many are in there if we don't know what the overlap is. So we don't, and we're also not going to be able to know how many are there. So I think with that information, we can now find out how many learners take science only, life science only, and geography only. Okay, so 32 take physical science. Okay, so let's go back down. Okay, so now physical science, everybody taking physical science. We're not saying what happens to your life science, etc. So everybody in that blue circle, there are 32 of them. Okay, and we've currently already got all those learners there. They're already there in the blue set. So that's 16, which means we've only got 16 learners that are only taking science. Okay. So if we write down here, physical science, we've got 32. Then we're not counting anybody twice. There's 16 who do science only. There are 8 who do science and life science. There are 3 who do science and geography. And there are 5 who do all 3. So they're taking some form of physical science. Okay, then we've got, let's choose this color. We've got 29. They take life science. So life science, they're 29. So in this pink circle, the event life science, they're 29. But there's this 5, there's this 8, and there's this x. So we've got to take those away from the 29, which gives us 16 minus x. Okay, take them all away from 29. And then finally, we've got, let's use, no, we've already got white. Let's use yellow. We've got 19 take geography. Grade 11, do you see how I'm using color? It's very important that you use and play with colors. And now I'm forgetting what I mean. 19. So in this yellow circle, there have to be 19, but there's already 8. So there will be 11 minus x. Okay. One thing about your sample space, we need to write down that the total is 65, that we're in the sample space. And do you remember how many students didn't take any subjects? 8 learners do not take any of the subjects. So those are all the learners that take the subject. So outside in the sample space in here will be the learners that don't take anything. So all those together with the 8 will give us the total of 65. Okay. Now let's find out what the value of x is. Well, I've just said that if you add all these up, you should get 65. So let's just go up there. So we're going to get our 16, our 8 is 24, and 5 is 29, and 3, 31. So that's my number, 31, plus our 16 minus x, plus 11 minus x, plus our x. Together, each of these students must add up to what? Well, it's got to add up to plus 8 must give us 65. So if we just add on an 8, it's going to give us 65. I know that you're thinking about alternative ways of doing that. That's fantastic. Okay, so if we add up all these numbers, okay, we're going to get a minus x plus x is 0. So we're going to get 39 and 16. We're going to get 11. 66. Just 8, 9, and 16, and 11. 10, 16, okay, 1, 3, 4, 5, 6. So it's 66. So we've got minus x is equal to minus 1. So x is equal to 1. Looks like x is equal to 1. Okay, so if we come back and we try and make sense of that x value, we're going to get one learner takes life science and geography, and we've got 15 learners, and we've got 10 learners here. And if we add up all these learners, we're then going to get the value. Now, let's just work through the same problem, but determine each of the following probabilities. The learner chosen at random will take physical science only. So if you want to know the probability of only physical science, okay, we'll write down probability of physical science would be how many physical science students are there? And we were told that there were 32 students, and what is the total number of students in the survey? There were 65. So that's the probability of the physical science students. What is the probability that the learner will take physical science and geography, but not life science? So can we go and find the situation where they're taking physical science and geography, but I must not include the life science as well? So can you think of which students we're going to leave out of our diagram? They've got to take physical science and geography, not life science. Let's go back to that slide. Okay, so they must take physical science and they must take geography, but they must not take life science. If I choose students here, they're only taking physical science. If I choose students here, they're only taking geography. So which students are taking physical science and geography? The overlap. But can you see they've asked me to leave out the life science students? So I've got to exclude those 5 because they do take science and geography, but they also take the life science. So therefore, it would only be 3 out of our possible 65. So the probability of physical science and geography would be, okay, probability of physical science and geography. We found that there were only 3 students out of a possible 65. So the probability is 3 in 65. And then the probability that the learner chosen will take life science and geography, but not physical science. Okay, so they will take life science and geography, but not physical science. Can you think of which students that will exclude? They must take both life science and geography. Let's go back to the Venn diagram. So we've got life science. They must take life science and geography, but they must not take the physical science. So that will exclude those students there. So therefore, if we chose students here, those would only do life science. And if we chose students here, those would only do geography. These students here are the ones that are taking both life science and geography, and we've calculated x as 1, so it would be 1 out of the 65. So that would be the probability of life science and geography. And sorry, here I should have actually included not life science, and over here, because that's another condition that we've been given, and not life science and geography, but not physical science. And we found that there was 1 in 65. Right, grade 11, these are lovely, lovely questions to work on, where you're trying to just sort out your data, that you're reading all this text, and how can you put it into a picture. Much easier to look at it on the picture form.
Thank you, Ms. Dina. Thank you, Mindsetters. Thank you, Macmillan, for proudly sponsoring our show. And have a great evening, Mindsetters.
Possible outcomes. So a synonym for possible outcomes is your sample space. Now, this concept, probability, is really the measure. So once we've got we've identified what our possible outcomes are, we've identified what our sample space is, the probability is that value. It's a measurement of how possible that outcome can be. So in this case, how possible or how likely is the event to take place? So it is a theoretical measurement. It's not like, for example, with your weather, whether you wake up in the morning and you think, oh, today's going to be a sunny day, but later on it's actually going to be a cloudy day. You're not measuring a predictability of the event. You actually want a number that measures a theoretical likelihood of that event actually happening. So with your coin, with your dice, there is some measure that you can have in terms of how. Let's look at what type of outcomes there are. So an outcome, just one, would be the result of a single trial of an experiment. So if I toss a coin and I get a head, that would be my outcome. I got a head. If I toss my coin and I got a tail, that would be my outcome as the result. The possible outcomes are all the possibilities that I can have. So, for example, if I toss a coin, I can have either a head or a tail. So my possible outcomes are a head or a tail. And those possible, if we're going to work with Venn diagrams later, they're also known as the sample space. So the sample space would be all the possible outcomes that you can have of an event. So, for example, if you were rolling a dice, you would get either a 1 or a 2, 3, 4, 5, or 6. So your sample space would be all the possibilities of the value of that dice. Those would be your possibilities. As I said, in this lesson, we're going to revise the definitions used in the study of probability. We're going to work with some Venn diagrams, and we're going to use contingency tables to establish whether events are independent or not. The first definition that you will see around probability is the word experiment. We often talk about an experiment, and that is a situation that will involve probability that leads to results, and the results are called outcomes. So every time, for example, if you throw a coin and you get a head, that would be known as an outcome. If you throw the coin again and you get another head, that would be another outcome. So the total amount of outcomes would give you what an event would comprise. So your event might be, let's toss a coin 3 times. That would be the event. The outcomes would be, what options do you have available to you when throwing that coin?
And if you haven't noticed, it's spring day. I brought a bit of spring here into the Mindset Studios with my little headband. So hope you guys are amped and ready. And let's get started with probability. Grade 11s, don't forget, this show was proudly sponsored by Macmillan. So let's go.
Thanks, Megan. Right, grade 11s, you may have done a little bit of probability already in grade 10, or you may not have done some probability. So in order for us to all be at the same place, I'm going to revise some of the definitions that we use around this topic, and then we're going to work through some examples around 2 of the most important topics around probability, and that would be working with a Venn diagram and then also working with two-way tables, which are also known as contingency tables. So to get us started, we are going to be doing quite a lot of dense text work where we're going to look at the definitions that we're going to be using, because obviously any game that's played, you're required to know the rules. Without the rules, you can't really understand the game, and so that's where we're going to go. Just go and try and learn some of the vocabulary around probability. So let's get to the slides.
Welcome grade 11s to our fantastic Monday show here at Learn Extra Live. You're here with me, Megs, and of course my lovely leading lady Dina. How have you been?
I'm feeling very well, Megan.
I haven't been here since February, so please excuse me for my rusty mathematics skills, but I'm so impressed that I'm here today. So what are we doing?
We are doing grade 11s, a little bit on probability. It's a very, very short period to try and cover all the grade 11 or the whole grade 11 topic. So we'll be really looking at the aspect of probability.
Okay, thank you. Well, let me tell you, previous show I didn't tell you where to get all your information. Ooh, naughty me. So I just want to tell you, you can go onto facebook.com/Learn Extra, as well as Twitter, which is @Learn Extra. And I know you mindsetters want to be there with the notes in front of you, and you can download them at mindset.co.za/Learn Extra.